All right, we only have 2 more sections before the test. And today is solving exponential and logarithmic equations. Tomorrow is some applications of exponential and logarithmic equations, and then the test is Thursday. So this is one of the first sections that I reviewed in this textbook when we were thinking of adopting a new textbook. And this is the section that made me go, he explains things just like I do. Because I remember when I learned exponential and logarithmic equations, I had all types of problems mixed together, and it seemed like every problem had a different trick. And that's a terrible way to feel about solving equations. If you think there's going to be a different trick on every problem, you just might tend to give up. But the way that Mr. Blitzer broke the problems down is the exact same way that I do it in college algebra. There are 2 kinds of equations we're talking about, exponential and logarithmic. You can tell the difference because logarithmic has the word log in it. Of those 2 types, there are 2 subtypes. So we're talking about 4 types of equations in all. Exponential equations, the 2, if you want to call it tricks, or the 2 tools is a better word for solving exponential equations, is either you can write both sides having the same base, or you can't write both sides having the same base. And we'll have to figure out what to do then. But that's our only 2 types of exponential equations. Either you can write both sides having the same base, or you cannot. Obviously, it's easier if you can write both sides having the same base. And then logarithmic equations, the 2 types are either get all of your logs on one side and constants on the other and change it to exponential form, or combine logs on each side so that you can just take the logs off and set their arguments equal to each other. So we'll look at those 4 types of problems, and I think the test probably has 1 of each type, so be looking for that. First, we'll talk about some exponential equations, and the very easiest ones are the ones where you can write both sides having the same base. So when I see 8 to the 1 minus x equals 4 to the x plus 2, first thing I think is, well, first thing is, this is an exponential equation. Second thing I think is, can I write both sides having the same base? Are 8 and 4 both powers of some common number? Yeah, they're both powers of 2. So in the place of, hey, Chastity, I thought you were taking the ACT today.
Yeah, I thought I did too, but she said I would have to make it up because there wasn't any more spots for registration.
Well, that's all right. I'd rather have
There's
you.
a makeup on the 15th, though. I just have to go through it before Friday.
Okay,
So.
all right. Well, I'm glad you're here. So number 1, we can write both sides having the same base. And I think we had a few of these in the very first section of exponential equations. We said if you have 7 to the animal equals 7 to the duck, what do you know about the animal? 7 to the animal equals 7 to the duck, then the animal has to be a duck. If you have the same base, you have 2 expressions equal to each other and they have the same base. The only way that they can be equal is if their exponents are equal. So if we can write both of these as having the same base, then we can just set the exponents equal to each other. The 8, we can put it in its place, 2 cubed. And the 4, we can put in its place 2 squared. Now, as long as I have parentheses there, that left hand base is still 8 and that right hand base is still 4. For them both to be base 2, I've got to remove the parentheses. And to remove the parentheses, I need to think, when you raise a power to a power, what do you do with the exponents? When you raise a power to a power, and exponent rules. You multiply the exponent. So to remove those parentheses, I'm going to multiply that 3 times 1 minus x, and I'm going to make sure to distribute it completely. So I had 2 to the 3 minus 3x equals 2 to the 2x plus 4. And after I have both sides having the same base, then the only way these two expressions can be equal to each other is if those exponents are the same. So 3 minus 3x equals 2x plus 4. And then you're just solving a linear equation. You can add 3x to both sides and subtract 4 from both sides and divide both sides by 5. And you get x equals -1/5. Anytime you solve an equation, you can check it. This one would be a little bit yucky to check into the original equation, because you'd have 1 minus -1/5 would be 6/5, and 8 to the 6/5 may not be easy. Well, I can't do 8 to the 6/5 in my head, but certainly if you check it back into this line where you had the same base, you'd have 3 plus 3/5 equals -2/5 plus 4. And I think that would turn out to be the same on both sides. All right. The most common mistake on these on the test is to forget that the first thing you should check is if you can write both sides having the same base. We're going to see in just a minute if we cannot write both sides having the same base, the process is uglier. So always remember to check that. What about the second one? Can you think of a common base I could use for the left-hand side and the right-hand side? I could write them both as powers of 7. The left-hand side already is written as a power of 7. And I could write the right-hand side as 7 to the what? You just want to make sure that every line is equivalent to the line above it. Work down the page and not across, and keep looking back up and going, yep, that's still equivalent to that. And now we have 7 to the animal equals 7 to the duck. So the animal has to be a duck. Just set the exponents equal to each other and solve that equation. You could multiply both sides by 12 to clear out the fractions. That's absolutely fine. Or there's a special process when you have one fraction equals another fraction. You remember what the name of that kind of equation is when you just have one fraction equals another fraction? Starts with a P. It's a proportion. This is a proportion, just a special kind of an equation. One fraction equals another. And the special way of solving proportions is the equivalent to multiplying both sides by 12. But to solve a proportion, you can just cross multiply. 2 times x minus 2 is 2x minus 4. 6 times 1 is 6. And once again, we're just solving a linear equation. This one's a little bit easier to check than the first one. If you let x be 5, 5 minus 2 is 3, 3/6 is a half, and a half is the same root. A half as an exponent is the same thing as square root. And then one more. I just don't want you to be phobic against e's when you see an e. I can still write both sides having the same base. How can I write the right-hand side? Left-hand side's good, but how could I write that right-hand side as just e to the something? Sure, I have negative 2x in the, as the exponent in the denominator. So if I flip it up to the numerator, it becomes negative 2x. And then I have an equation where both sides have the same base. I can just set the exponents equal to each other and solve that. You want 20 of those on the test? That's the easy kind, when you can write
Yeah.
both sides having
Yeah,
the same base.
20 of
What,
those.
Cassidy? Cassidy, what'd you
20
say?
of those exactly.
It's a little bit harder when you cannot write both sides having the same base. So let's deal with that. It's still, this number one is still an exponential equation because you don't see a log in it anywhere. The first thing I would think is, can I write both sides having the same base? And I don't think so. There is one thing that seems kind of obvious as what I should do first. What would you do first? Yeah, I get the exponential expression by itself. I may not be able to figure out what to do after that, but I think it's reasonable to add 7 to both sides. 11,250. All right, unless I can squint hard enough to figure out a power of E that gives me 11,250, I can't write both sides having the same base. So can you think of anything I could do? You know, solving equations is all about undoing what's done. If that's 7 subtracted, I want to add it to both sides. If something's multiplied, I want to divide both sides. So what I'm thinking here is I need something that will unexponentiate that 4x minus 5. What tool do I have that unexponentiates?
Can you take natural log of both sides?
Yeah, technically I could take log base anything of both sides. I could take log base 2 of both sides if I wanted to, but it wouldn't really make sense to do that because if I want to undo base E, it would be easier to take natural log of both sides. Natural log of E to the 4x minus 5 equals natural log of 11,250. And what does that do for us on the left-hand side? When I take natural log of E to the 4x minus 5, what's left? Just the 4x minus 5, because natural log and E undo each other. Just another way I could think about it to show you that there are several ways to think about it. I could bring that 4x minus 5 out front. If I brought that 4x minus 5 out front, all I'd have left right there is natural log of E. What's natural log of E?
One.
It's 1. Log base 2 of 2 is 1. Log base duck of duck is 1. Log base E of E is 1. So if I brought that 4x minus 5 out front, I'd just have 4x minus 5 times 1. All right, it's easier just to say natural log and E undo each other and leave me the 4x minus 5. And then what 2 things would get the x by itself? What 2 steps? Add 5 to both sides and divide by 4. That would give me x equals, I'll write the 5 first, 5 plus natural log of 11,250 divided by 4. Now, on the test, any problems that didn't come out to be whole numbers or terminating decimals, fractions, I've asked you to give me the exact answer and a decimal approximation. I want you, this is the exact answer. And I want that because if you punch it wrong on the calculator, I still want to give you partial credit for having done all the work right and just punched it wrong on the calculator. So make sure you give me the exact answer, and then for an approximation, I think I tell you what to round to, maybe 4 decimal places. Let's make sure everybody knows how to do this on the calculator. The big thing would be if you want to divide both of those terms by 4, then you either need the whole numerator in parentheses or brackets, or you can kind of punch this thing backwards. Some of you have the fabulous frontwards calculator. Some of you have the cursive backwards calculator. The fabulous frontward calculator, you enter the natural log and then the 11,250. Cursive backwards calculator, you have to have the 11,250 on your screen before you hit natural log. So you probably know by now which one you have. Go ahead, and I didn't bring this answer with me. So if 2 or 3 of you agree on the answer, we're going to call it right. But everybody punch it. I want to make sure you know how to do that on your calculator. Do you have something, Silas?
Yeah.
What do you have?
3.5820.
Okay, so let's see if everybody gets something close to 3.58.
Got that too.
That's what you got, Dominic?
Yeah.
Okay, so I'm feeling pretty good about it if Silas and Dominic got that. Silas, would you repeat those 4 decimals, 3.5?
5820.
All right. Make sure everybody can get that. Good. Got it, Dominic? Ready? You have your calculator. Okay. Okay. Jordan, did you get that? Awesome. Chastity? Chastity, did you get that?
Yes.
All right, good. All right, that one wasn't bad. Taking the natural log of both sides unexponentiated the 4x minus 5, and it was pretty easy to solve for x after that. Now these are getting progressively more difficult. That was the easy one. What about number 2? Actually, to make sure I have plenty of room, I'm going to start it up here. First thing I would ask myself is, can I write both sides having the same base? Because if I could, that would be the very easiest way to do this problem. If that right-hand side was, say, 125, then I would solve this by writing both sides as having the same base. But since it's not, I'm wondering how to unexponentiate an x minus 3. I know I could use log base 5 to unexponentiate, but I don't have a log base 5 button on my calculator. I could use the change of base theorem, but if there's something I can do, if there's some way to just use either natural log or log so that I can punch it on my calculator, I think that would be best. Any, mini, miny, mo, you have a preference? What to do to both sides? Hey, read the directions in the homework. On the test, I would count either one right, but in the homework, if it says solve using natural log, then take the natural log of both sides. If it says solve using common logs, then take log base 10 of both sides. You'll get the same answer either way for the decimal approximation, but the exact answer will look different. I'm just going to take natural log of both sides. Natural log of 5 to the x minus 3 equals natural log of 137. Taking natural log of both sides is another one of those things that's legal to do as long as you do it to both sides. And then it's not quite as easy as this problem was because I can't say natural log and 5 just undo each other. Like I said, natural log and E just undo each other. So what can I do? Well, it looks like I made the problem harder. Why did I do that? What property can I use on the left-hand side?
Change of base.
I could, but I don't have to because I have that property of logarithms that says log of something to a power. I can bring the power out front. My goal was to unexponentiate that x minus 3, and I have a power that says I can just bring it out front. Now, I meant to make the most common mistake and leave off those parentheses. If I had left off those parentheses, that would indicate that only the 3 had been the exponent of the 5. I've got to have the whole x minus 3 in parentheses. And then what do you think we would do next? Let me grab a pencil and write something that I can erase real easily. As scary as that looks, it's really just like 5 times x minus 3 equals 137. I am not suggesting that you can just erase the logs, but I'm saying you solve these two equations the same way. What would be the first thing you did on this easy baby equation I made up? Yeah, you'd clear out the parentheses. Well, here you have to distribute a natural log of 5. Make sure you multiply it by both terms. X natural log of 5 minus 3 natural log of 5 equals natural log of 137. All right, let's go back to our little baby equation for a second. And this got me through a whole lot of math in college. If I had something big and scary and I couldn't figure out what to do with it, I made up something little and cute and just say, well, what would I do to both sides here on this easy equation? What would be next? Yes, you would get your x's on one side and the constants on the other so that you could combine like terms. So what do you think we need to do to both sides here? That's just a constant. It's an ugly constant, but it doesn't have an x in it. There's only one term with an x in it. It's x natural log of 5. So I want it on one side and everything else on the other side. Add 3 natural log of 5 to both sides. If I did that to my little baby easy equation, what would be the last step? On this equation? Yeah, y'all need to wake up and help Dominic. He's carrying more than his share of the load here. So what do I have to do on this ugly equation? Instead of dividing by 5, I'm dividing by natural log of 5, but it's the same process. Divide both sides by natural log of 5. And that's your exact answer, but it's probably not the easiest way to punch it on the calculator. And I checked in my labs to see if it would take this as the exact answer or the simplified version of that as the exact answer. What I mean by simplified version is if I could put that numerator back together as just a single logarithm, it would be much easier to punch on the calculator. How could I put that back as a single logarithm from last night's homework? It would be natural log of what?
Five to the third plus 137.
Do you put the sum of two logs back together as a sum?
Oh, no, it's the product. It's the 5 to the third times 137.
Right, right. You can put this back together by putting the 3 back as the exponent of the 5 and then multiplying it by the 137. The log of or the sum of two logs can be written as the log of a product. That's a little bit easier to punch, or somebody do this for me. What's 125 times 137? Silas, you have it?
17,125.
Thank you. That's actually what would be easiest to punch on the calculator. I think, because I tested it, I think that my labs would either take this or that as your exact answer. And then as your decimal approximation, somebody punch that and give me 4 decimals. Anybody have it? Anybody second that? Okay, it's
I
way
got
bigger
that
than I
too.
could do in my head. I knew it was gonna be something bigger than 1. That's about all I could do in my head.
I got that too.
Okay,
Yeah, I did it as well.
awesome. Anybody having trouble getting that? Okay,
I have one quick question.
yes, sir.
In the second step where it's like x minus 3 times ln 5, before we distribute,
Uh-huh,
okay, so just while I was waiting, I just divided ln 137 divided by ln 5, and then I added 3 to that, and I got the same answer.
yes, you could absolutely do that. That's perfectly fine. I think that would be a little bit harder to do on this next one,
Okay,
but it would absolutely work on this one. And on the next one, I'll tell you why it would be a little bit harder to do what you did on this one.
okay.
Yeah, what you did was perfectly legal. All right, like I said, these getting just a little bit uglier each time. There it is. Undoing base E was easy because taking the natural log of both sides undid the E. This was a little bit harder because taking the natural log of both sides didn't just undo the 5. But it still wasn't too bad because we just had a constant on the right-hand side. What if we had both sides being exponential equations? Now, let me say something about this example 4 and example 5. Y'all know how much I love this book. I'm going to do one of these and one of these and say, if you need another example, examples 4 and 5 are excellent in the book. And out by the side of each step, Blitzer tells you exactly what he's doing in blue ink. So make sure you look at these 2 examples in addition to the 2 that we're going to try to do. I don't know why I said try to do. I think we can do it. All right. First thing I think on number 3 is it's an exponential equation. As soon as I think that, my second thought is, could I write both sides having the same base? And I'm actually praying a little bit when I say that. Oh, please, can I write both sides having the same base? Not easily. I can't think of a power of 3 that would give me 7. So, any ideas? Anything we could just try? Say that again. Yeah, to unexponentiate, I have to take the log of both sides. I can use log base anything I want, but it really only makes sense to take log base something I have a button for on my calculator. So I'd either take natural log or log base 10. And in my math lab, I'd read to see if they told me which one to use. On the test, doesn't matter. All right, so I like using natural log just because it has fewer letters. And for just a minute, it looks like I made the problem worse instead of better. What was my purpose of taking the natural log of both sides? Why did I do that, Silas?
Bring the exponent.
Yes, and when I do, oh, I can make the most common mistake here. And Chastity's right. Whenever I say, okay, I made the most common mistake, what is it? It usually has something to do with parentheses. If I want to indicate that that whole 2x plus 1 was the exponent, I have to have the whole 2x plus 1 in parentheses. Same thing on the left, right-hand side, I need the x plus 2 in parentheses. Now, Dominic, the reason that what you did on this problem was perfectly okay, but would be less helpful here is if you divided both sides by natural log of 7 and divided both sides by x plus 2, it just wouldn't look as clean as what you had on your third step on number 2. You can see that?
Yeah.
Okay. So here, instead of dividing and having a rational expression on both sides, I'm just going to clear out the parentheses. Distribute the natural log of 7 on the left, distribute the natural log of 3 on the right. Hey Brady, I'm just curious. I write small. I try to leave enough space there for people who write a little bit bigger than me, but some people would probably take a half a page to do that. Your note-taking app, does it let you automatically add space if you need it? Or not really? If you're just writing, okay, but you have to write very small. You have to fit it in the same amount of space that I have. Okay. Okay, sounds good. So what next? What was our next step up here after we got rid of the parentheses? That's it. I want my x's on one side, my constants on the other. So right here, it doesn't matter which side my x's end up on and which side my constants end up on. I try to move things to the side that'll leave me the fewest negatives. All right, I would prefer to get my x's on the left just because that would involve one negative. Actually, this problem, it would involve 2 negatives no matter which side I got things on. So I'm just going to get my X's on the left and my constants on the right. And here's where this problem, another place, this problem's a little bit harder than the previous one. In the previous one, we only had one term that had an X in it. So when we got that term on the left and everything else on the right, all that was left was divide by natural log of 5. The reason this one's a little bit harder is X is part of two terms and they're not like terms, so I can't combine them. Any ideas? Absolutely. That's what we do when we have X as part of two terms we can't combine. I can just factor out an X. Then I can just divide by all that stuff in parentheses. And that will be my exact answer. I think my labs would take that as an exact answer. I'd have to be really careful entering it on my calculator because I'd have to have the whole numerator in parentheses and the whole denominator in parentheses. And most calculators now, when you press natural log, it will automatically open a parenthesis and I have to close the parenthesis. So I'm going to have a lot of parentheses in this if I enter it on the calculator just like that. It would be much better, much easier to enter on the calculator if I wrote the numerator as a single log and the denominator as a single log. Tell me what I would have if I wrote the numerator as a single log. Natural log of not, you don't put the difference of two logs back together as a difference. You put the difference of two logs back together as a quotient. So it wouldn't be 9 minus 7, it would be 9 over 7. Is that okay, Dominic? The property that we had yesterday said I can put, it was, oh, got it? Okay, all right. And Miss Chastity did the same thing up here a minute ago. She started to put the sum of two logs back together as a log of a sum, and that's not correct. Sum of two logs is log of a product. Difference of two logs is log of a quotient. All right, and then the denominator as a single log would be natural log of what? That gives me something that's much easier to enter on the calculator and even easier to type into my lab. That's my exact answer. And then a decimal approximation. Somebody give me one. I think this is going to be negative, isn't it? Okay, let's play like I didn't say that then. It's not a negative, it's something smaller than 1. Okay, what'd you get, Silas?
0.0900.
0.0900. Is that, did I hear you right? Okay, so darn close to exactly 0.09. Any questions? All right, one more exponential, and I need to pick up the pace just a little. That is unlike anything that I've solved before. If I didn't have that -12 there, I could just move one of the two to the x's over and I'd have both sides having the same base. That'd be nice, but can't do it. Let me show you what this is kind of like. This helped me in a lot of math classes too. Again, this was too ugly to deal with. And what was bugging me was the 2 to the x. So I thought, if I just put ugly in place of 2 to the x, then this would be ugly squared. 2 to the x squared, just ugly squared plus ugly minus 12. What kind of equation is that? Because of the highest exponent being 2. It's a quadratic equation. How could you solve that quadratic equation? By factoring? You think I can factor something this crazy? I think maybe I can. And I'm still confused by that 2 to the 2x, but looking up here, I'd just say factors of 12 that have a difference of 1 are 3 and 4. And to get a +1, I'd have to have a +4 and a -3. So I'm just wondering how to factor that 2 to the 2x. You have any ideas about what I can put here and here that would multiply back together to give me 2 to the 2x?
2x.
2x or 2 to the x?
Oh, 2 to the x.
Yeah, remember the wonderful thing about factoring is I can write down whatever you say in pencil and check it. If that doesn't turn out to be right, all I have to do is erase it. No big deal. But let's see if that's right. 2 to the x times 2 to the x. When you multiply two expressions with the same base, what do you do with their exponents? And x plus x, sure enough, is 2x. Outer, I have 4 uglies. Inner, I have -3 uglies. And that leaves me 1 ugly. And we already checked the -3 times 4 gives me -12. So that's right. If I have 2 factors multiplied to give me 0, then either the first factor has to be 0 or the second factor has to be 0. The first one, just add 3 to both sides. Second one, subtract 4 from both sides. And what do you already know about this equation on the right? What power of 2 would give you -4? Well, since we're solving an equation instead of undefined, you would say no solution. This just doesn't have a solution. What about this one? What could I do to solve for x? That's how we unexponentiate. So that we can bring the exponent out front. And the exact answer would be x equals natural log of 3 divided by natural log of 2. And then you could give me a 4 decimal approximation. Anybody have it?
No, yeah.
0 after that if I want 4 decimals? Okay, that's okay. All right, that's exponential equations. First, ask yourself, can I write both sides having the same base? Because you can see that these 3 problems at the top were easier than the next 4. So if you can write both sides having the same base, that's what you need to do. Actually, I could have done these 3 problems the same way. I could have on number 1, I could have taken the natural log of both sides, brought the exponents out front, worked and worked and worked. But as soon as I came up with this fraction for an answer, I would have gone, oh, I didn't need to do it that way. It's okay, but that was the hard way to do it. Easiest way would have been to have written both sides as base 2. All right, the 2 types of logarithmic equations are either you have a single log on both sides and you take off the logs, or you have log equals a constant and you change it to exponential form. Changing it to exponential form is what Blitzer calls use the definition of a logarithm. That just means change to exponential form. Sometimes there's a little bit of work to do before you can change it to exponential form, but that's going to be our way of getting rid of the logs. The other kind he calls using the one-to-one property. The one-to-one property is what says if log of animal equals log of pig, what's the animal? Yeah. If you have 2 logs with the same base set equal to each other, the only way that that can be a true statement is if the arguments set equal to each other. So it's kind of like this. We're trying to get both sides written with the same base so that we can just take the logs off. All right. I don't think we're going to finish all of these, but let's get a few of them. One other thing to watch out for. When you solve logarithmic equations, or let me back that up. When you solve rational equations with fractions in them, you have to make sure after you work and work and work and you get a proposed solution, you have to make sure that your solution doesn't make any of the denominators 0, right? Because if it does, you just have to mark it out and go, well, that was nice, but I can't use it. Similarly, when you solve logarithmic equations, you have to make sure that whatever you get for a possible answer doesn't make any of the arguments negative, because you can't take the log of 0 or the log of a negative. Let's say, make sure it makes, let's see, be sure to reject any value that's not in the domain of the function. And what that means is makes the argument 0 or negative. It makes the argument 0 or negative, we can't use it. Regardless of which one of the 2 types of logarithmic equations you have, if you have logs that are already on the same side, oh, here's a typo of the day. I can't solve that with 2 different bases. and I'm not sure which one it was supposed to be. One of them will be much easier than the other. I don't know what it was supposed to be. Let's make them both log base 6. Otherwise, this is a much harder problem. All right, so on the left-hand side, if we put those back together as a single logarithm, we would have log base 6 of what? The sum of 2 logs can be put back together as the log of a product. Now is when I can determine which one of the 2 types I have. Something I could write up here by objective 4 is logs on both sides. If I have logs on both sides and I can get a single log with same base, I should say single log on both sides, then I can just take the logs off. But that's not what I have in this first example. I have log on one side and constant on the other. That's my clue to change to exponential form. What would that be in exponential form? The base would be Tyler, I changed both of those to 6s. Got it? Because if one of them's 6, one of them's 2, I got a whole different problem. But if they're both 6s, then I could change that to exponential form. The base would be 6. The exponent would be what? Ooh, I'm a little bit worried about y'all if y'all can't change that to exponential form. 6 to the first equals the x plus 3 times x plus 4. And then I'm just solving a quadratic equation. Now, you can't say x plus 3 equals 6 or x plus 4 equals 6. You're solving an equation by factoring. You got to have a 0 on one side. So I'm going to FOIL out that right-hand side, x squared plus 7x plus 12. And then I'm going to subtract 6 from both sides. And I think I was probably right. Both of those were supposed to be 6s because this will factor. Yay, I don't have to use the quadratic formula. I would get as my 2 possible solutions, -1 and -6. Do I mark both of them out and say, oh, the answer to a log equation cannot be negative? That's not what I should be saying. It's not true that the answer cannot be negative. The answer cannot make the argument negative. So what about the -1? Could I use -1 in both of these original arguments? -1 plus 3 is positive. -1 plus 4 is positive. -1 is fine. What about -6? As soon as I see -6 plus 3 is negative, I know that I can't use that one. Makes the argument negative. So my only answer is -1. All right. 3 minutes, yikes. Well, example 2 is, I'm glad this one's next because it is the other kind of logarithmic equation. Regardless of what type of a logarithmic equation I have, my first step is try to get a single log on each side. If I have logs that I can combine, like on the left-hand side, it's not the left-hand side, that's the right-hand side. I could write that as log of 2 times 2x plus 3. Because the sum of 2 logs can be put back together as log of a product. And this is the 1-to-1 property. If log of 5x plus 1 equals log of 4x plus 6, then 5x plus 1 has to equal 4x plus 6. And then I'm just solving a linear equation. Does that 5 make any of the arguments negative? No, so it's good. All right. We only got one side of the notes done. I tell you what, there are examples in the book just like these. If nobody has started the homework, which I think I started it, I fixed it so you couldn't start it early. I'm gonna look for a video like these, but I'm gonna take the word problems out and put them on tomorrow's homework since we didn't get them today. So your homework will be solve logarithmic and exponential equations. And if I don't find videos like these, then you look at the examples in the book. They're good. All righty, see you tomorrow.